Okay, so we're done with the review. Let's start now with section 4.3. And we're gonna discuss we're gonna start with second order linear homogeneous ODE with constant coefficients. And the keyword here, well, linear homogeneous is definitely a keyword. The keyword here is constant coefficient. So this small method works only for linear ODE, linear homogeneous ODE, where the coefficients are constant, not function of x. So the form is ay second plus by prime plus cy equal to 0, where a, b, c are real, and a is different than 0. Okay. Now recall that linear homogeneous, in the case of order 1, i.e. I have ay prime plus by equal to 0, the solution is, so ab real, and a different than 0. The solution are y of x equal a e to the minus b over a x. Do you agree? Let's see. So if you solve it, this is y prime over y equal minus b over a. So this is log y equal minus b over a log y prime. So absolute value of y equal e to the minus b over a x plus c, and you know how to proceed. Okay, so this is for b and a real number. Okay, if b and a are not real number, then you would have to do something else here, because b of b over a is a function of x. Okay, then so let's call this star. Okay, okay, motivated by the first order case, we look for solution of the form y equal e to the mx. This is not the only reason. There are more reasons to do this, but I just motivated it for the first order. Now, how many solutions I need to start? This is a linear homogeneous ODE, so I need two linearly independent solutions in order to generate all the solutions. This is from section 4.1. Okay. So I look for solution y equals e to the mx, y equals e to the mx. Notice that y prime is m e to the mx, and y second is m squared e to the mx. So what I'm trying to say here is that y equal e to the mx is a solution to star, to the ODE star, if and only if, replace now in star, you get ay second, which is am squared e to the mx, plus b m e to the mx, plus c e to the mx equal to 0. So maybe I should write star here just for you to remember. But this if and only if, now simplify by e to the mx, if and only if m solve the quadratic equation am squared plus bm plus c equal to 0. Now this is called auxiliary equation. So I'm starting with ay second plus by prime plus cy equal to 0. And I'm saying that I have a solution of the form e to the mx if and only if m solves the following auxiliary equation, which means if m solves this equation, then y equal e to the mx is a solution. This is an if and only if statement. Now the auxiliary equation was, to solve the auxiliary equation, second order, I calculate the discriminant, or I just factorize the discriminant delta equal b squared minus 4ac. And I have three cases. So case 1, delta is positive, which means which means the auxiliary equation, which means the auxiliary equation has two real simple roots, m1 equal minus b plus square root of delta over 2a, m2 equal minus b minus square root of delta over 2a. Two distinct real simple roots. When I'm saying two, I mean they are distinct. Two put in this distinct real root. Why is it called simple? Because if m1 m2 as a solution, I can write am squared plus bm plus c as a into m minus m1 m minus m2. Okay, so this here is a power 1, so this is why we call them simple. They are real and they are two distinct real simple roots. This implies that y1 equal e to the m1 x and y2 equal e to the m2 x are two solutions to the ODE star. They are also linearly independent. Why? Because I proved from section 4.1. I already proved in section 4.1 that e to the alpha x, e to the beta x are linearly independent. E to the alpha x, e to the beta x are linearly independent for alpha different than beta. So this implies, so I have two linearly independent solutions to a second order ODE, so I'm done. This implies that y equal c1 e to the m1 x plus c2 e to the m2 x is the general solution to star. This is the first case. Now case 2, delta equal to 0. Then the ODE, then the auxiliary equation has one real double root, m0 equal minus b over 2a. Why? Because I can write it as a times m minus b over 2a squared. Okay, it's real, it is double. Then y1 equal e to the m0 x is a solution. So this method only gave me one solution. How many solutions I need? I need two solutions. How do I find? Here in the first case, I already have both of my solutions. This is done. But here this method only gave me one solution. How to find the other one? We find y2, a solution y2 that is linearly independent to y1 using the reduction of order method, which is what we learned in 4.2. I will use the formula here directly, but for you to train on the method, redo it from scratch, as we did the first example of section 4.2. So I have y2 equal y1 integral e to the minus integral p of x dx over y1 squared dx. Now remember, my ODE is ay double prime plus by prime plus cy equal to 0. What is p? In order to know p, I have to, the leading coefficient should be 1. Here the leading coefficient is a. So this is y double prime plus b over a y prime plus cy equal to 0. So this is scratch. So p of x is b over a. So I get y2 is equal e to the m0x times integral e to the minus integral of b over a dx over e to the 2m0x dx, and this is e to the m0x integral e to the minus b over a x over e to the 2m0x dx, but recall that m0 equal minus b over 2a. So this is equal e to the m0x integral e to the minus b over ax over e to the minus b over ax dx. So this is now equal to 1. So this is equal e to the m0x integral dx, which is equal x e to the m0 x, by suppressing the constant, because remember I only need one solution. So this implies that the general solution is y equals c1 e to the m0 x plus c2 x e to the m0 x. Now case 3, delta is negative. This implies that the ODE, well, the auxiliary equation has two complex simple conjugate roots, which are m12, this comes in a couple. So this is minus b plus or minus I square root of minus delta over 2a, which I can write it as alpha plus or minus I beta. These are conjugate. One is alpha plus I beta, the other one is alpha minus I beta. So this implies that y equal e to the alpha plus beta I x is a complex solution to the ODE. And this implies that real of y and imaginary of y are two real solutions to the ODE. This is by the review. The only lemma by the lemma of the review. Remember, here the ODE has constant coefficients that are real. Okay. Now, what is the real of y? What's the imaginary of y? So this is y1 equal real of y, y2 equal imaginary of y. But notice that y, so notice that y equal e to the alpha plus beta I x. This is equal e to the alpha plus beta I x. This is equal e to the alpha x times e to the beta x times I. And this is equal e to the alpha x from Euler formula, cosine beta x plus I sine beta x. This is from the review. So this is equal e to the alpha x cosine beta x plus I e to the alpha x sine beta x. And this is y1 and this is y2 without the I. So this implies that y1, which is equal e to the alpha x cosine beta x, and y2, which is equal e to the alpha x sine beta x, are two solutions to the ODE, and they are linearly independent. Check with the Wronskian. Okay, I will not. I mean, we showed that cosine beta x and sine beta x are linearly independent in section 4.1, but now they are multiplied by the same number or by the same function, so they stay linearly independent. Okay. So you can say this is from 4.1. If you're not sure, calculate the Wronskian, okay, and show that it's different than 0. So this implies that the general solution is y equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. So if I find two complex roots, which is, for example, which are here, alpha plus I minus beta, so e to the alpha x cosine beta x is a solution, e to the alpha x sine beta x is a solution, and the linear combination is a solution. I'll do 3 examples for going to the general higher order. So examples. Let's solve y second minus y prime minus 12y equal to 0. Okay. Now in this case, so this is linear, homogeneous, constant coefficients. So what is the auxiliary equation? It is what is here 1 times y second, so this is m squared minus 1 times y prime minus m minus 12 equal to 0. Okay. And now I calculate delta and I solve, or I try things. So if it has, so if I can write this as m minus a times m minus b, then you will have a times b equal to 12, correct? So if I have integer solutions, they should be divisors of 12. And now what are the divisors of 12, please? This is a method that is useful in general to guess. I mean, here you don't have to guess, you can calculate delta, so can calculate delta and proceed. Now what are the divisors of 12? The divisors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay. Now I need two numbers whose product is 12. So they can be 1 and 12, 2 and 6, 3 and 4. But I also have that the sum of the solution in this case is 1. Correct? Because the sum of the, if you expand the thing, this is m squared minus a plus b m plus ab. Okay. Again, this is useful in higher order. In second order, you can just calculate delta. So I know what. So a plus b here equal 1. So the product is 12 and the sum is 1. Okay, and then by trying, you can see that m squared minus m minus 12, this will be, so the product is 12, the sum is 1, so it's definitely not 1 and 12 and 2 and 6. This, I mean, plus or minus 2, plus minus 6. So you should look here. Okay, so this will be m plus 3 into m minus 4. Okay. Then m1 equal minus 3, m2 equal to 4, are two real simple roots. Then y1 equal e to the minus 3x, y2 equal e to the 4x are two linearly independent solutions. And this implies that y equal c1 e to the minus 3x plus c2 e to the 4x is the general solution. Okay. Now 2. Let's solve 9y second minus 6y prime plus y equal to 0. So the auxiliary equation in this case is 9m squared minus 6m plus 1 equal to 0. Now you can notice this is an identity or calculate delta if you want. But I mean, you should be, if you are, you shouldn't be too rusty in calculation. So I mean, second order ODE, second order polynomial, you should be able to do some calculation noticing identities. Okay, you have been trained on this in high school. Okay, even before. So this is 3m minus 1 squared equal to 0, and this implies that m equal 1, 3 is a double root, real root. And this implies that y1 equal e to the 1 over 3x and y2 equal x e to the 1 over 3x are two linearly independent solutions. By the way, how do I know linearly independent here? So we proved it. Another way to know linearly independent here, other than calculating Wronskian, is to check that y2 over y1 is not a constant. These are two solutions. So this is enough for linear independency in case of two functions. So these are linear independent solution here, and this implies that the general solution is y equals c1 e to the 1 over 3x plus c2 x e to the 1 over 3x. Now 3. So I have y double prime plus y prime plus 1 equal to 0. So the auxiliary equation is m squared plus m plus 1 equal to 0. Okay, now if you want to calculate, use all these tricks we did before, you will notice that you will get nowhere. So I will be stuck with calculating delta. So what is delta here? It's 1 minus 4 times 1 times 1. It's equal minus 3, so negative. So I have two simple complex conjugate roots, which are m12, it's minus b, so minus 1 plus or minus I square root of 3 over 2, which is minus half plus or minus I square root of 3 over 2. Okay? Then what is my alpha here? It's minus half. What is my beta? I choose one of them. It's enough to choose one of the two solutions. Square root of 3 over 2. Then y1 equal e to the minus half x cosine x square root of 3 over 2. And y2 equal e to the half x sine x square root of 3 over 2 are two linearly independent solutions. As I told you, because the ratio here is not a constant. And this implies that y of x equals c1 e to the x over 2 cosine x square root of 3 over 2 plus c2 e to the x over 2 sine x square root of 3 over 2. Now the book, in this case and in this case, take the exponential as common factor. I don't like it a lot because I want you to see here that this is my first solution, this is my other solution. This is my first solution and this is my other solution. Okay, I will stop here and continue in the next video.